This is multiplexers. So I'm using electronic workbench. Electronic workbenches, by the way, is on all these computers. It's a really neat application that allows you to simulate circuits with schematics. So what I have is I have a multiplexer. Then I've got a digital pattern generator. So this is a pattern generator. So what I'm doing is my pattern generator is basically counting from zero to FF, or from 0 to 255. So if I'm counting, but it outputs a binary output. This is a binary output right here. I'm not using all the outputs. I think this does 1, 2, 3, 4, 16 bits. I'm only using 8 bits. And then I'm bringing this into a multiplexer. Looks like a 74, like 157 or something like that. But it's a 4 to 8 multiplexer. So what's multiplexing? Come on, guys. What's multiplexing? Now don't read. Reading something is, so right now we should know. That would be like me saying, what's your name right now? And you take out your wallet and look your name up on your billfold and say, my name is Charles Richard Raymond. Media. Of course, in digital, the media is going to be copper wire, right? You understand? But multiplexing, we use multiplexing all the time. Sometimes because we have to, sometimes because of the cost of doing it any other way. And I think we was talking about the cable TV. If they was to have to, every station was to have to run their wire to your house, that would be unmultiplexed. Wouldn't be much for them. That'd have two, but coming into your house, you'd have one. Yeah, a lot. So so it would be too expensive to try to do it. So but a media could be a lot of things. Of course, primarily the media is either air or going to be wire, or copper wire. So most of your TV stations use either or. A lot of your broadcast stations, your local channels usually provide both of them. They send it through the air, and they also send it through cable. Of course, it's digital now. Your signals are digital, but you can go out and buy a digital antenna. You can still receive all the channels, channel 6, channel 13. I don't think Fox broadcast or not. They do broadcast. When channel 42 was originally, no, it was broadcast. It was a UHF channel. So what does multiplexer do? Well, it saves, in computers we say it saves hardware, right? And of course in computers, if you can touch it, it's hardware. So what I have is I have a signal generator right here. This is just counting from 0 to FL, or 0 to 1111111. And then we're outputting on these lower things. And I'm bringing these into my multiplexer. So if I'm counting, then this will give me, my input frequency would be divided by 2, divided by 4, divided by 8, divided by 16, divided by 32, right? Then I've got a logic analyzer here. A logic analyzer, basically, it's not really an oscilloscope. It can be. But a logic analyzer lets us look at digital signals. So we got 2 of them here. We've got one was pretty cheap. I'll show y'all that. It hooks up to a regular scope. It's really neat. And then we got a high dollar one that can be either used as a digital storage scope or as it can be used as a logic analyzer. I'll show you both of them. But this is simulating a logic analyzer. So this is the logic analyzer, and what it does, it lets us look at a lot of information at the same time. So I have my logic analyzer hooked up to the data inputs, and then I have this one right here hooked up to the multiplexed output. So when I turn it on, I'll try to turn it on if I can get to it. So you see my logic analyzer, ain't that neat? So this is a 16-channel logic analyzer. Now this one right here is showing me the output of my multiplex. So basically all this is would be divide by 2, divide by 4, divide by 8, divide by 16. And all it's doing is just taking a signal and just dividing it down, right? You understand? So right now, this is channel 0 down here. And when I look at the select on my multiplexer, I have all the, so here's my ADC selects. And of course, like I said, when you see ADC on it, or AD, something like that, on as the names of the pins on these chips, then the first thing you probably need to think about is weighted binary, right? You understand? So ADC, that would be give me the ability to select 8 different inputs, and the inputs are called D0 through D7. So right now I have ADC connected to 0. So this is my select switches right here. These are my pull-up resistors. So like we told y'all, normally when we use a switch to input into digital, we've got to put a true 0 and a true 1, right? You understand? So how do we do that? Well, we just take a switch, and when it's turned on, what we say is on, it connects this to common, and then this resistor would drop all the voltage. But when I turn the switch off, then it's going to pull this up to that pull-up resistor is going to pull it up to a true 1, right? Y'all understand that? Are you okay with that? Yeah, let me draw it. Let me come back and I'll bring up PowerPoint. And so we're used to light switches doing stuff like this. Oops, I didn't want to open my mail. I wanted to open PowerPoint, and mail looks a lot alike. Where's my PowerPoint? I guess I can get it from there. So I come over here and I've got a logic gate. Okay, so I got a NAND gate. And just for the heck of it, well, let's just use an inverter. So if I come over here and I take a switch and put it right there, and I hook this up to 5 volts, what's the gate see? Is it seeing a high or is it seeing a low? What's the gate see? It's seeing this right here. It's seeing nothing. It's not a high, because if it was a high, it would be 5 volts. If it was low, it would be ground. So it's seeing nothing. Now, TTL usually assumes that as a high. But I didn't say always. I said, well, usually. And when we look at the inside of the gate, we can probably figure that out. So that means if I had the switch open, I would get a low. If I had the switch closed, I would get a low. Out of TTL. Now, another logic like CMOS. CMOS will see it as anything when we get into CMOS. CMOS sees a floating input as anything. I can start bringing my finger close to the input and it'll start switching. So CMOS, you never, ever leave inputs floating. Good design is never use a floating input. We don't call it a nothing, by the way. We call it floating. So if I want to put a true high and a true low into a digital logic gate, then we're going to have to come up with another way that we do it. Call it floating. That's what they call it. I call it a floating input because it's a nothing. It's not a high and it's not a low. So in digital, we don't use the term nothing. We call it float. So how am I going to get a true high and how am I going to get a true low out of a switch? Well, what we'll do is we'll come over here and do it a little different. So I'll come up and put a resistor, and I'm going to connect it up to VCC, which is plus 5 volts, right? Okay. And then I'm going to come over here and I'm going to take my switch and I'm going to put it like this. So now if the input, now if I open the switch, there's nothing here, there's no current flow through the resistor or very little. For a high, it needs about 400 microamps. So if that's a 1K resistor, how much would it drop? It'd drop nothing, right? So you can take 400 microamps. Normally that's what the input of a TTL gate, it requires about 400 microamps for a high, usually less. So that means that's this VCC, which would be plus 5 volts, would be sitting right there. So your gate would see it as a what? Would see it as a high. Now when I come up here and close that switch, now I'm connecting the bottom of that resistor to common. So this common is going to be felt right there. This is going to go to 0 volts. Now my 1K resistor would drop the applied voltage. But it's 1K, so you know, I is equal to V over R, so I would be equal to 5 over 1K, or I would be equal to 5 milliamps. 5 milliamps is almost nothing, right? You understand that? So it's not going to hurt the resistor. But now I get a legal low into it, or I get a legal high, depending on the position of the switch. And by George, we can look at the trainer and look at those switches, and this is the way they do it. They do it a little different. I don't like the way they do it, but basically it's the same. So we can't just bring a switch into a digital gate, because it's got to see a legal high and it's got to see a legal low. So this is the way we bring switches into gates.
So you turn it on, you make it legal low.
Right.
Then when they're on,
that's exactly right. So this is what we're doing when we do that. I mean, we can look at the print on the trainer. We'll do that in a little while. We can just really need. They do it a little different. The way they do it is that one switch can affect another switch. Normally we have every switch. And what do we call this resistor right here? We call it a pull-up resistor. So if the switch is not closed, well, when the switch is not closed, then it pulls it up to what? Pulls that input up to a legal high. So that's what I'm doing right here. So here's my pull-up resistor, a 1K pull-up resistor. Over there on this side is what? 5 volts. And then the other side of the switch is connected to common. So right now I would be putting in all what? I would be putting in all lows into the select input, which is going to select input 0. So input 0 should be going through and coming out of the Y output. So here's input 0 down here. This is showing me my output. Here's input 0. So which one is going to the output? Input 0. Now if I go over here and put a 1 in there, then this output should switch to this guy, right? You understand? So I'm going to come over here. How would I put a 1 in here? Well, I'm going to come up here and take the 1 that represents 0. So this is the 0. This is the key pin number. So this is A, B, C, and it says I'm going to hit the number 1 key. That's the way it's programmed to do. So I'm going to hit the number 1 key, and notice that switch changed position. So now I'm getting a 1 on there. And notice what output did it switch to? Well, it switched to this one right here. So this is my output. I'm showing this is the output. See there? So now the second one is going through to the wall, to the output. I come over here and I'm going to turn 1 off. I'm going to turn 2 on. Now this is 2 right here, right? This is 0, 1, 2. Now this should switch to the 2 out. So now the 2 is going, now the 2 input is going to the output. Y'all see what see this? Okay. Now here's 1, 2, 3. So when I come over here and put a 3, so this would be a 3. Nope, that would be a 3. Nope, that would be a 3. So 0, 1, 2, 3. This should go to the output. So that needs, so whatever I put on the input of the multiplexer, that's the input it allows to do what? To go to the output. Which one do y'all want to see? I mean, I can go to any one of them. So we'll go up here and go ahead and do 7. So that'd be 7 right there. So now this one up here at the top. Oops, I meant to stop. Excuse me. So here's number 7, and this is the one going to the output. So what I'm doing is I'm selecting which input is passed to the multiplexed output, right? And that's a multiplexer. So if I was over here instead of me flipping switches, if I was to put a counter on the input, it would automatically switch between the 7, the 8 input. Now what I'm doing over here is I'm demultiplexing. So notice, I'm sending 8 signals on how many wires? No, not 1, 4. 1 data wire, but then I'm sending the select. So when I select an input over on my multiplexer, I'm telling my demultiplexer which one to select. So right now I got a 7. Can you see which one's flashing? Real slow because it's divided by. And if I come over here and go back to a 0, it's going to start flashing real fast because 0 is oops, wrong thing, Rich. So here's 0. And notice which one is flashing now. But it's flashing real fast because it's a real. So there's 0. There's 2. Here's 3. No, there's 4. So there's 3. No, it's not 3. Rick. All right. I'm not going to. So this is 0. No, this is sorry. Yeah, this is 7. This is 0. Right. This is 1. Okay. This is 2. Here's 3. You got to remember we're counting from 0. 0, 1, 2, 3. So 3 is actually what? 4th one over. And of course this would be 7. I'm just going to skip on up. We can't even see 7. There we go. Because it's flashing real slow. So what I'm doing here is I'm taking 8 signals. I multiplex them onto a wire, a single wire. Whichever one I select to send, I send the select over to my demultiplexer. And what does it do? It demultiplexes. So what I'm doing is I'm sending 8 signals on 4 wires. I can send 16 signals on 5 wires. But every time I've only got 1 data wire, right? You understand? I could send 256 signals on 9 wires. Through the 8 plus data wire. So this is what multiplexing is all about. Multiplexing is saving these wires running between the 2 pieces of equipment. So this is another 74138. It's a decoder, but we looked at it a while ago. We looked at it the other day, and it says it's a decoder demultiplexer. So what I'm doing is I'm bringing my select over to the ABC outputs, to the ABC inputs. My gate signals, these are what's required to enable it, right? You see that? I just have those connected to a common or ground. And then I'm bringing my data in on the high active G1. So every time this gets enabled, the data goes high, it's enabled, and then this right here selects and it allows it to go through. Well, this is what multiplexing is all about. What type of multiplexing is this? Is time domain multiplexing or frequency domain? Well, if it was frequency, we would have multiple signals on there at the same time. How many signals do I have on here? One, add a one. Fine. So what advantage does broadband have? Well, broadband, you're guaranteed bandwidth. A baseband, you're not guaranteed bandwidth. It's only when you get your time, right? You understand that? Of course, I'm selecting time here. The Ethernet is a time-based, is a baseband network. And of course, we don't send the signals that selects because it's inside that addressing information is inside the packet. But what they do on baseband is they put one packet on there, and then they come off. We used to compare it to the old party line. When I was a kid, when the phone rang, well, what it is they would send out a unique ring. So you had a unique ring when somebody was trying to call you. You could pick it up and you could sneak up and hold down on the thing and bring it up and you could listen to people talk all the time. But that's what you were supposed to do. So how did you know when it was time to call somebody? Well, you'd pick up the line and you'd listen. If there's nobody on it, you'd do what? You'd dial. If there was somebody on it, then you'd listen to their conversation. Now you're supposed to hang up and do what? Check it again. And that's what, so Ethernet uses something called carrier sense, multiple access with collision detection. So that's what it does. So it's sitting right there, right now. Everybody's sitting there looking at the network. If there's nothing on the network, as soon as you hit something on there, you send the packet. It sends the packet back to you. And then you release the network. And if two guys try to get on there at the same time, which it happens, they collect, if they detect a collision, in other words, if they get garbled data, they both back off. And then they have what they call a random number generator in there. So each one of them generates a random number, and then that determines when they come back on. And sooner or later, you'll get time. So, but if baseband, if nobody's on the network, you get the full bandwidth of the network. So if you're on a gigabit network, and nobody else is on it, by George, you get what? You get a gigabit. If there's 100 people on it, then you get 100th of that, right? You understand that? A baseband or broadband, you're guaranteed time. You're given a certain range of frequencies, and you're modulated at a certain frequency. And then you got all these people riding on the same line, same place at the same time. Most of the time. If you see the bandwidth, though, everybody go slow, right? So broadband is when we modulate it, we place the data on a carrier. We have all these people out there sharing it at the same time. Baseband, how many computers can be inside the subnet at any one time? One. It used to be bad when we had things called hubs. Now we have use smart devices called switches. Switch, what it'll do is it'll route you to another computer. The other computers can keep talking as long as they don't come to the same computer. Now on Ethernet, the route data, we use switches. And then routers are divided up into what we call subnetwork. So my subnetwork won't interfere with somebody else's subnet until we try to get into their network. Right? So like trying to get it to a server or something like that. So this is multiplexing, guys. Pretty neat, huh? In this digital, we use, in digital circuitry, we use time domain multiplexing. So your microprocessor, what does it use? Microprocessor. How many things can it communicate with at any one time? That's all the microprocessor can do. One thing. Which is kind of misleading. We're dealing with 64-bit processors, but the data bus is actually 128 bits. So basically, you can have two things on there at any one time, but each one of them's only got their own 64 bits. But it's time domain multiplexing. That's what the process is used. And that doesn't use for IO. IO is still, I don't know if they've ever gone 32-bit on IO. So it was 16-bit for a long time before they started adopting digital. The 128-bit bus is for memory. I can tell you why I'm telling you that. So, okay, on multiplexers. I think the test that we're having next week, as far as it goes, is the multiplexer. I know y'all did 2 lectures. Y'all did one on flip-flops. This is real neat. What do you think about flip-flops? Probably not tonight, since the test don't cover that. So basically, we had those 2 big lectures in a row. So basically, our lectures are a little above, a little ahead of what we need to do. What we're hurting at is lab, huh? Yeah, it is, but we had to cover a whole 3-hour class. Those are long lectures. So that's why I split it up, to give y'all credit for attending. Normally what we had done is we'd have been in a lecture part of the class and lab in part of the class. So yeah, they were long, guys. I understand that. If you don't, you understand, it takes special people to take online classes. Now they do have some classes. They do have the college has 2 online PE classes. Yeah, because they have a totally online, they got a business associate's degree that is totally online. It's a temporary quiz for those 2.
Yeah, we do online. I think
Oh yeah, they're back for the lectures. Yeah, they're back online. I put them back on. Oh really? 7's not on there? Okay.
No.
What's that? Oh, 9 is the characteristics. Yeah, that's gonna be.
Yeah, it's not bad.
Okay, I'll put it. Yeah, we turn off all those quizzes between classes. So, well, I mean between classes, not between. So the last time I taught digital, you turn off all the quizzes, when they come past due. So we don't leave the quizzes up all semester long. Okay, guys, y'all okay on multiplex and demultiplex? Now this is covered in that first lecture, decoders and multiplex. Everybody okay on decoder? Yeah. Oh, we basically did the whole lecture. The only time I think I showed y'all is this right here. I just added this tonight, by the way. And electronic workbench is really, really neat. Can you imagine wiring this up? So every one of these would be a what? Would be a wire. So digital, it's not hard to wire. It just takes a lot of wire because you're wiring up a lot of circuits, right? You understand? You still have to pass this. So if I was doing this with discrete logic or transistors, and I built up all this stuff, we would still have these same wires, plus the wires connecting the circuit. So the wires actually connecting the circuit are inside these multiplexers. But what you got to learn is that once we get past exclusive ORs and exclusive NORs, all your combinational logic uses rectangles. So how do you know what's what? Well, after a while, you learn to recognize the names of these pins. This is what we call a pinout, right? So the pinout is when we give the pin, we say, okay, this pin is hooked up to the A input. Of course, y'all dealing with pinouts. Y'all dealing with pinouts now. It's very, very important to understand that. Well, after a while, you start recognizing these things, like these enable pins. They're going to be labeled G's, they're going to be labeled S's, they're going to be labeled C's. So, an S is for strobe. Then the Y's and the Z's and the Q's, the high letters are usually outputs, right? And the low letters are what? Usually inputs. Now, ABCD, when you see this, when you see these ABCDs, and what you need to do is start thinking weighted binary. With A being the least significant bit, and then whatever it goes up to being the most significant. So I know this is 3-bit inputs right here, and then ABCD means I can put 8 different combinations. So after a while, you learn to pick up on. So notice here on the outputs, they're using Y and Z. Y and W. This doesn't show up real good, but W does it. Is there a little bubble on there? Or a bar? No, it's not. W is the inverted output. I don't know. There's a G right there. I need to look that one. By the way, electronic workbench can't do an overstrike. So see the little apostrophe? That indicates a low accuracy. Of course, they got the little bubbles over there. Well, I'll have to look on this and see what this is. But that's the multiplexer. And then this is the demultiplexer. But it's actually a decoder that I'm using as a what? The multiplexer. Just about all your decoders, except for the 7447, which is the BCD to 7-segment decoder. Are you okay? Any questions? Yes, no? All right, guys, let's go to lab.